Good morning. This is a lesson on antiderivatives. So up until now, we've been doing only derivative calculus, and things have been getting pretty heavy with our applications. This is kind of a step back and kind of take a deep breath and breathe a sigh of relief, because this material should be pretty easy. So just to kind of recap, back when we first started to do derivatives, we learned the power rule. Now we did the limit process on the secant line. We're not going to worry about that, but we're going to just refresh our memory here. So if we had x squared, we're going to take the 2. It's going to become a coefficient, and then the exponent is going to drop down by 1, right? For x to the third, it's going to be 3x squared. X to the fourth, 4x to the third. The square root of x, which is x to the half, it's going to become 1/2 x to the negative 1/2. 4 over x cubed becomes 4x to the negative 3. These are equivalent, and then I take the derivative, which gives me negative 12x to the negative 4th. Okay, that's all simple derivatives, and it's really what we just need to remember for this new stuff. We're not doing anything complicated. We're just kind of thinking, oh, well, that was the first stuff that we learned when we started doing derivatives. Okay, so we're taking the derivative and we're using the power rule. Well, the next step is to learn about antiderivatives. So antiderivatives are going to be starting with this column of stuff and working our way backwards. Now, normally we would spend some time, we would develop the rule. I'm just going to tell you the rule. It is right here. Okay, so if this is the function that we're trying to take the antiderivative of, this is the rule. So notice this is f prime. Now this is f, so we're undoing the derivative, it's the antiderivative. So notice that n now is n plus 1, and that n plus 1 is now dividing our original. So again, in words, the exponent goes up by 1, the coefficient is divided by the new exponent. So let's try it right here. Again, I'm going to rewrite the rule because it's so fresh for you guys. A n to the x goes to a over n plus 1, x to the n plus 1. So very simply, we're going to take our exponent. We're going to increase it by 1. We're going to take our coefficient. We're going to divide by that new coefficient, and we're going to simplify. So we get 3x cubed here. Now what I would like to do is say, okay, if we took the derivative of this is a new function. I'm going to call it capital G. Okay, lowercase g was 9x squared. If I take the derivative of capital G, I should get lowercase g. Do I? Use the power rule for derivatives. So we're going to multiply 3 times 3, which is 9. And we're going to reduce the exponent by 1, which gives me 2. Is that the original? Yes. That's how we find the antiderivative. That's the process. Let's talk about notation before we do the next problem. You've probably seen this symbol before. Now we're going to use it. This is called the indefinite integral. We'll do definite integrals later. And all that's asking us to do is find the antiderivative of this function, and the dx means with respect to x. So as long as this function is in terms of that variable, we're good to go. So I'm going to call this lowercase f. I'm going to rewrite the fifth root of x as x to the 1/5. I'm now going to apply the power rule. So I'm going to increase the exponent by 1. That's adding 5/5, so it's x to the 6/5. And I'm dividing by 6/5, which I can multiply by the reciprocal. Now there's one component of this that we're not really looking at. And that comes from, I'm going to kind of come back to the other problem over here. Let's just say I had 9x squared plus 7 as a new function, h of x. If I took the derivative of that, back up. If I had 3x cubed plus 7 as a new function, h of x, and I took the derivative of that, h prime, I would get 9x squared plus 0. So notice that that is the same as g prime. So what we're kind of doing here is we're going to basically get all kinds of different possible answers here. So in every time that we do a problem, we're going to add plus c to that. Okay? We're going to add plus c, not to this, sorry. We're going to add plus c to the antiderivative. It is called the constant of integration. Okay? The constant of integration. So every time I do the antiderivative, at least for the time being, we're going to do plus c, which is the constant of integration. Because when I take the derivative of my answer, I should get the original problem. 6/5 times 5/6 is 1. X to the, subtract 1 from 6/5, and we get 1/5. The derivative of any constant is 0, which gives us our answer. So that is the basics. I'm going to talk about some properties here. If you have a situation like this where you have the sum or difference of different functions, now that seems complicated but really isn't. Example would be like 3x squared plus 2x minus 1. Then you could break that up into its component pieces. So we can have that component plus that component minus that component, and then we would do the antiderivative of each piece, and that would be the answer. Now I like to just jump right into using the power rule for each piece here. It doesn't matter which way you do it. Now, taking a look at just this one piece right here, it doesn't matter if I looked at this as this. I can factor out any constant term. I can bring it right outside of the integral symbol. It doesn't matter. Now also, don't forget your basic rules. Now there are plenty more, but if you have the sine, the derivative of this cosine, well guess what? Now we can go backwards. If you have your derivative chart, or you find a derivative chart, if you know the derivative, now you can take the antiderivative just by going in the opposite order on this chart.